Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video describes the 3 basic rules for making nonlinear regression models. Let's get started. So to begin, we need to clear up some key concepts relative to nonlinear regression. We've mentioned in earlier mini lectures how not everything in the real world can be modeled with a straight line. It would be wonderful if we could just make a linear model for everything. And we try to make linear models wherever we can. Sometimes we actually transform the data so that it will fit a linear model. However, this isn't always the best approach to take. And not everything in the world can be transformed to become a linear model, so we need to have methods for finding nonlinear functions that fit our sample data. So in the previous mini lectures, we've been looking solely at linear relationships, whether that had one independent variable or multiple independent variables. In this and the next few mini lectures, we're going to look at providing a brief introduction to regression using nonlinear relationships. And of course, we're just going to go straight to the software, the StatCrunch. We're not going to, we could go in if we wanted to and look at the old school methods for doing this, but hey, we're all going to use the software, so let's just focus on that, all right? So, 3 basic rules are identified by your textbook author for identifying a good statistical model. Now, we're going to go over these rules, and then I'm going to show you some I would call them slight quibbles that I have with these rules based on my years of experience actually making nonlinear regression models out in industry. The first item that your textbook author goes into is to look for a pattern in the graph. Examine the graph of the plotted points, compare the basic pattern to that of generic models. Next, find and compare values for R squared. Models that result in larger values of R squared better fit the observed points. And third, use common sense. Don't use a model that leads to predicted values known to be totally unrealistic. It's not that these rules are bad. It's not that these rules are wrong. They're actually pretty good. But there's some detailed nuances that it just doesn't seem to address. And that's where I come in with my experience and say, yeah, we're going to adjust these rules slightly. So my experience in the real world leads me to make the following adjustments to these 3 basic rules. First, you want to compare patterns in the graph with common uses for generic model types. So typically when you're working out and making these models in the real world, there are some model types that will fit your model data, your data for your sample better than others. Okay, so for example, if you're looking for burnout in electronic equipment, you're pretty much going to go with an exponential model. Okay, that's how it's modeled because, you can make it with some other distribution, but hey, the exponential distribution tends to fit that data best. So you tend not to look at the other model types. You're going to see the pattern in the graph, of course. Making the scatter plot is still going to be the first thing you do to make sure that you've got that basic shape for your model, but you're typically not going to mess around if you see that basic shape with other models because, it's just what's done in that particular field. Second, we're going to look at adjusted R squared and not R squared. Okay, as we've seen previously, the adjusted R squared values, they account for differences in the number of variables in the model as well as differences in sample sizes. They allow us to have a level playing field even though the models don't come from the same playing field. So we're going to look at adjusted R squared values and not R squared. Third, again, you want to use good judgment. Okay, common sense is one thing, good judgment is something else. So, of course, if the model's producing a value that's unrealistic, you're not going to use it. But if that really is your model, you should strive to provide more rigor so that it produces a more realistic value. So go back and look at the assumptions. Go back and look at the data Go back and look at your boundary conditions. Go back and look at everything you used to produce the model and say, what can we do to make these values better so that the model we produce is better? It's the old adage of garbage in, garbage out. So if your data is really dirty or you're missing a lot of data points, well, you might want to look at that. Fill in the blanks. Go see what you can do to find the missing data. Or is there a way you can estimate the missing data to get a good prediction out of the model? Again, if you've got data points that are known to be, bad, don't be using them in the model. Take them out. Again, this is where good judgment comes in, okay? Common sense is just looking at the prediction and saying, yeah, you don't want to use the model if it's totally unrealistic. But good judgment would say, hey, if your model's unrealistic, let's go back and see what's wrong with the data that's giving us the unrealistic model to begin with. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.